So the ionic compounds and acids dissolve when you put them in water. When the way they dissolve is to fall apart into the ions. So when I write NH42SO4, there is none of it in the solution because the NH4 and the SO4 fell apart from each other, because that's how they conduct electricity. Let's make sure this works. So remember, this was the test we did. I put water there. The light bulb doesn't come on. But if I throw some salt in the water, I don't have any salt sitting here. Oh well. We'll use baking soda. Use baking soda in the water. Let it dissolve. It's still not on. Was I too safe? Where is my power? Oh, this would be why it's not on. I was extra safe and unplugged it. So the baking soda will make it come on if I have everything put together right. There we go. The baking soda makes it come on. Okay, and pure water wouldn't make it come on. So what's going on with that baking soda and water? Well, I think I found an animation that shows us that. Okay. So, it's going to play, it's running slow, it talks at you. Okay, so here's what happens when you put salt into water. Okay. What happens is the salt is sodium chloride, and the light bulb comes on because, come on, show me those ions, that the salt is ions in a pattern, and the water comes on and hangs onto it. The positive end of the water, the H's, hangs onto the negative piece. The negative part of water, the O's, hang on the positive piece. And it separates the positive and negative pieces so they can move by themselves. That's what conducts electricity. Okay? Now, I said we talked about that dissolving as a partial thing. I don't want you to think it's absolutes. We'll talk more about it later. But HF, we say would dissolve in water. But when it dissolves in water, HF dissolves in water, only a very few of them, they stay together for the most part, but only they've got 1 out of 10 fell apart there. Okay? It makes a few ions, so it conducts a little bit. So that would be, we would call a weak electrolyte. And if you put something molecular, like CH3OH, that's what this is, put something molecular in there, molecular doesn't have to fall apart into charge pieces. It can stick together and be dissolved. So that's CH3OH, so it's got O and H, so it can hydrogen bond. So the OHs, with their positive H's and their negative O's, are going to be able to hang on to other CH3OHs with hydrogen bonds. That the hydrogen on this one is attracted to the oxygen on that one. Okay? So that's what holds them together in a liquid, is the hydrogen bonds. But when I pour water in, come on, throw in some water, the water can hang on to the whole molecule, so I don't get separate charges. So this will dissolve but not conduct. That's what sugar does. It dissolves, but it doesn't conduct. Okay, so in order to conduct, you have to have free-floating ions, and water can tear those ones that dissolve into ions. Okay? So the reason why the light bulb went on is because there were ions there. Okay? So when we write them as aqueous, we say they're dissolved in water. They're really not there. there really is no NH4-2SO4 in the solution. It is falling apart. If I write NaCl aqueous, there's no NaCl. There's Na plus and Cl minus. So as we said, NaCl is really Na plus and Cl minus, and that's why it can conduct when it dissolves in water, because the Na can go to the negative electrode, and the Cl can go to the positive electrode. That's what happens. Is the Na plus goes to the negative, the Cl minus goes to the positive because opposites attract, and that's what's moving when you conduct electricity. Those whole ions are moving. Okay. So, and it doesn't matter if they got subscripts. K2SO4, aqueous, is really K plus and SO4 2 minus. Because the ion K is going to make is going to be K plus. The 2 is there because it takes 2 of them to make SO4 equal 0. But when they're by themselves, they don't have to have exactly the right numbers. I got some K plus. I have 2 K pluses for every SO4, 2 minus. But the ions are going to be K plus and SO4 2 minus, so it's going to conduct electricity. If I dissolve that, it would conduct electricity. So ionic compounds conduct electricity because ions move. So that's proof that none of this is true. Okay? So what do you do about it? Okay? When scientists look at other planets, the first thing they look for is liquid water. Okay? Because they can't think of a way for life to happen without water being there, without a liquid being there. Because what water does is it tears the individual ions away from each other so that they can get to each other. That while I'm hooked to one thing, I can't react with something else. So the water tears them apart. So things that are solids things that are liquid and things that are gases aren't separated. So this is what's really happening in a double replacement reaction. I have ions all through the solution, and if they change, if you're making solid or gas, you're taking those ions out of the solution. The ions are disappearing. So you're using up some of those ions to make the solid. So you got fewer and fewer ions in solution. That's what's going on. It's actually the ions that interact, not the whole chemical. So if we want to completely describe what's really happening, we need to write the complete ionic equation. Complete means everything's there. Ionic means everything's an ion. So the complete ionic equation is going to have everything, if it's an ion, as an ion. Okay, doesn't need to start a conversation when you get here, Christian. Okay. So every aqueous compound is written as separate ions. And solids, liquids, and gases as whole compounds. So the complete ionic equation is an attempt to describe what's really in the dish. So here's the kind of equation we wrote yesterday. Magnesium chloride and lead 2 sulfate makes magnesium sulfate and lead 2 chloride. Okay. But every place where it says aqueous, that stuff's not really there. Okay? Every place it says solid, it is really there. So what's really in the dish is there is no MgCl2. It's Mg2 plus and Cl minus. I can get their charges right off the table. That's what ions are in magnesium chloride, magnesium ions and chloride ions. There's not really any PbSO4. Instead, it's Pb2 plus and SO4 2 minus. Because it's aqueous, there's really no MgSO4. There's Mg2 plus and SO4. I forgot my 2 minus there. Oops. But PbCl2 was a solid, so it's not separated. The solids are shown together. So all I did was take MgCl2 and said, what ions are in MgCl2? Well, Mg's a 2 plus, Cl's a 1 minus. What ions are in PbSO4? Well, SO4 is 2 minus, so I can use that to figure out the lead had to be 2 plus. What ions are in MgSO4? Mg2 plus and SO4 2 minus. And PbCl2 is a solid, so it stays together. So anything that's aqueous, tear apart into its ions. Okay. So this is the one we saw yesterday. FeBr3, or not yesterday, the day before, the stuff that made the FeOH3. So let's take this double replacement reaction and turn it into a net ionic, or complete ionic equation. So, in my solution, is there really any FeBr3? It says aqueous next to it, so there's not really FeBr3, so I know Br is 1 minus, so I can figure out that the Fe has to be 3 plus. So what's really there is Fe3 plus and Br minus. All I did was take the FeBr3 and say what ions there are. So instead of it being iron 3 bromide, it's iron 3 ions and bromide ions. Is there really any KOH? It says aqueous, so nope. So the ions in KOH are K plus and OH minus. Is there really KBr? It says aqueous, so it's really K plus and Br minus. Is there really FeOH3? Well, yeah, it's sitting at the bottom of the test tube, right? So that you can see what happened here was the Fe3 plus and the OH minus got together and got removed from the solution. The K plus and the Br minus are still there. Does that make sense? Yeah. So, an interesting example. Let's do one more because this has got something I can show you that actually will show that what I'm saying is not just a bunch of words and diagrams. We'll actually watch light bulbs show us that it's true. Okay. So, barium hydroxide and H2SO4 make barium sulfate and liquid water. So is there really any barium hydroxide? For some reason, at one spot it won't let me draw. There's really barium 2 plus ions and OH minus ions. Is there really any H2SO4? Well, it says aqueous, so there's not any. It's H plus and SO4, 2 minus. Is there really BaSO4? Well, yeah, it says solid next to it, right? So BaSO4. Is there really any water? Well, yeah, there's really water. Water's not ionic. So I keep the solids and liquids together. So this explains that this I can show you a demonstration that shows that this is really what's happening. Okay? Here, I have a solution of barium hydroxide. Turn it back on. What happened to my light bulb? Turn on my light bulb. Okay, that worked. Oh, my barium hydroxide. Why is my barium hydroxide not working? It's bizarre. Somebody change my barium hydroxide. Do I have any more? Magnesium, sodium hydroxide, zinc. Yeah. Had it ready to go. Should have worked. What's going on? Somebody dumped the wrong stuff in there? Yeah, somebody dumped the wrong stuff in there. Okay, because my H2SO4 does good. I just got to get some barium hydroxide. So, I think I see it back there. Oops. Oops. Caught something. Calcium. Yeah, barium hydroxide. Here we go. All right. So, here's the barium hydroxide. Put some in this dish. Add some water. Give it a stir. Unplugged everything. Just trying to be safe. Okay, so let's stir that up. This is actually an automatic stir on the bottom. So as it stirs up and it dissolves more, I get more and more ions. It's got a little magnet that's stirring at the bottom. That's all it is. Okay? So the barium hydroxide is barium ions and hydroxide ions. Everybody okay with that? Okay. The sulfuric acid, the H2SO4, is H plus ions and SO4 2 minus ions. The light bulb comes on, right? Okay, so now I'm going to take some of the barium hydroxide and add and actually do that reaction. So let's do it here. clean up my dishes. My barium hydroxide was ready to go. Okay, so we'll add the barium hydroxide. Get it down the water so the light bulb comes on. Okay, and to that I'm going to add the sulfuric acid. You'll notice, see carefully that the it's almost there. That there's a, it won't make that bend for me. Ha. That as I do this, the bottom of my solution has gotten cloudy. Why would the bottom of my solution get cloudy? Well, I'm supposed to make a solid. So the white stuff you see at the bottom is the barium sulfate. But as I add the sulfuric acid, the light goes out. Why did the light go out? Well, when I react them, how many ions are left? Are there any ions on this side? No, there's no ions. If there's no ions, it can't conduct electricity. If I add more sulfuric acid, more H2SO4, okay, I get the light bulb to come back on because now I got extra H plus and SO4 2 minus because I added more of this. If I add a little bit of barium hydroxide back, I can turn it back off as it reacts with, so the light bulb goes off when I've added equal amounts of barium hydroxide and H2SO4. Because when I put them together, they make things that aren't ionic. If I put too much H2SO4 in, I get my light bulb back. I put too much barium hydroxide in, I get my light bulb back, because those are ions. Okay? So it's not just a bunch of letters on a screen. I picked this one because usually you don't get both of them together. I had to work really hard to find a chemical where I could get a solid and a liquid. Okay? Usually you have some ions left over. So if you think about the last one, you had some ions left over, right? That you didn't use. So the last equation you wrote was this, right? So now let's look at this a little bit differently. Okay? Oops, sorry. The K plus and the Br didn't change in this reaction. They were there at the beginning, and they were there at the end. So they weren't involved in the actual reaction. They have a name for things that aren't involved around the action that's happening. And the name for that is spectators. These are called K plus and Br minus are the spectator ions. Like a spectator just watches a game, these ions are there, but they're not involved in the reaction. They were there in the solution when we started, they're there in the end. The reason the light bulb went out over here is because that reaction had no spectators. Everybody was involved. Okay? But in here, K plus and Br minus didn't do anything. And in chemistry, we do something they don't do with spectators at sporting events. We eliminate them. Okay? If they didn't do anything, why write them? So all that really changed, if I get rid of all those pieces, is that Fe3 plus grabbed some OH minus and made FeOH3. And I can balance that by putting the 3 in front of OH minus. Bugs me when it's not balanced. Because that's what really changes. That's all that really changes. So chemists found they can ignore the stuff that doesn't change. And when they ignore that stuff, it's called not the complete ionic equation because it's not complete anymore. We got rid of pieces, right? If we got rid of pieces, it's not complete. So we call it the net ionic equation. And net has a meaning that you're going to learn to accept, not like. Okay? When you get a job, let's say you make $10 an hour and you work 40 hours a week. At the end of the week, they hand you a check. It is not for $400. You don't get a $400 check because other people get their hands on your money. Federal tax, state tax. These people called FICA take your money. That's Social Security. But your check is less than $400. And what they call the actual pay you take home is your net pay. Net is what you really take home. Net ionic equation shows only those things that really changed. So when we wrote that Fe3 plus OH minus makes FeOH3, that is the net ionic equation. We only include the things that really changed. So we do what you're not allowed to do at sporting events. Eliminate the spectators. Unless there was a soccer team in Italy where the fans were so bad, they actually said, you can have a home game, but you're not allowed to sell tickets. And they played the rest of their season in an empty stadium. So they did eliminate the spectators. Now, we're used to balancing it in terms of mass. That's how we've been balancing. But now, we actually have to look at charge. Because if the charge is different on the two sides, then you created or destroyed electrons. And not only can't you create or destroy atoms, you can't even create or destroy parts of atoms. So you can't create or destroy electrons. So when I put that 3 in front of FeOH3, I was doing it to fix the OH minus, keep my 3 OH minuses. But if you look, it also fixed the charge. Because Fe is 3 plus, OH is 1 minus, and there's 3 of them, that adds up to 0. The other side adds up to 0. Okay. So let's look at the process for changing an equation into a net ionic equation. It's everything we just did today. Find the ions, eliminate the spectators, write down what's left. Okay. No, I don't want this one. There we go. Let's try this one. Aluminum plus iron 3 sulfate makes aluminum sulfate and iron. So the things that are aqueous and ionic fall apart. Okay? So in this equation, is aluminum an ion or by itself, or what's aluminum going to look like? It's going to be a shiny piece of metal, right? So the aluminum is really there, right? It's a solid. It can't fall apart into pieces because it is a piece. Hey, FeSO4, is the FeSO4 really there? Well, it says aqueous, so that means it fell apart. The ions are Fe and SO4, but I need charges. So I look up SO4, it's 2 minus. Sulfate is 2 minus. If sulfate's 2 minus, then the Fe had to be 2 plus. On the other side, is there really Al2SO43? It says aqueous. So that means it's fallen apart. It's ionic, it's fallen apart. So the ions are Al3 plus and SO4 2 minus. Notice I didn't care how many there were. I just want to know what the ions were. So I didn't bring the only subscript I brought down was the one for SO4 because that stays together. Okay, and iron, does iron fall apart? No. So there's my complete ionic equation. It's got every kind of thing that's an ion is an ion. Now, to turn it into net ionic equation, we eliminate spectators. SO4 was on both sides. So I'm left with Al plus Fe2 plus makes Al3 plus plus Fe. Now that looks perfectly balanced, right? 1 Al, 1 Al, 1 Fe, 1 Fe, everything's great, except this side has a charge of 2 plus, and this side has a charge of 3 plus, which means I lost an electron someplace. I can't lose an electron. The two sides don't have to equal 0, they have to equal each other. So where are 2 and 3 going to run into each other? At 6, right? So if I put a 3 here and a 2 here, that makes them both 6. But that means I'll have to balance the mass now by putting a 2 in front of aluminum and a 3 in front of iron. So now my left-hand side is 6 plus and my right-hand side is 6 plus. It's the same charge. Now, those numbers are not random. Okay, if I went back up to the top and balanced the original equation, that's what I'd have, right? I'd have to have 3 FeSO4s, 2 ALs, and 3 Fes, because I needed 2 ALs over here and 3 SO4s. So if you look, the coefficients for iron and aluminum are the same, and there would be 3 Fe3 pluses and 2 Al3 pluses. So they are the same numbers. Okay. So potassium carbonate and magnesium iodide solutions make solid magnesium carbonate and potassium iodide. So is there really any K2O? Nah. It's really K plus and CO3 2 minus. Is there really any MgI2? No, it's Mg2 plus and I minus. Is there really MgCO3? So solid, so yes. Is there really any Ki? It's aqueous, so it's K plus and I minus. That's the complete ionic equation. Everything that could be torn apart is torn apart. Then net, get rid of the things that show up. K shows up on both sides. I minus shows up on both sides. So I'm left with CO3, 2 minus. But excuse me, folks, the bell does not dismiss you. Makes MgCO3. Okay, actually, if you think about it, if that's the only thing I made, that's the only possible net ionic equation. Because how do I make that solid? I put together the ions. Okay? So homework's out of the book. Don't do D on 25 and 26 because we haven't learned that yet. Have a good day.